Hi everyone and welcome back to the channel. Today we're diving deep into one of the most important architectures in modern deep learning, the transformer. We're not just going to talk about it, we're going to implement it from scratch in MATLAB using nothing but the mathematical equations from the original paper. And we'll use a super simple example, predicting the next number in the sequence 1, 2, 3, 4, 5, 6, which should be 7. By the end, you'll understand exactly how transformers work under the hood. Here's what we'll cover. First, what is a transformer and why it's so important? Then I'll show you the complete architecture diagram from the paper. After that, we'll break down every single component: input embedding, positional encoding, multi-head attention, feed-forward networks, and the residual connections. We'll walk through the MATLAB code that implements each piece, and finally, we'll look at the results, seeing our model correctly predict the number 7. Feel free to skip ahead using the timestamps in the description. So, what exactly is a transformer? It's a neural network architecture introduced in the 2017 paper, "Attention is All You Need" by Vaswani and colleagues at Google Brain. The key innovation is something called self-attention. Unlike older models like RNNs or LSTMs that process data step by step, transformers look at all positions in the input simultaneously. This is a game changer because it allows the model to capture long-range dependencies directly, no more forgetting what happened 20 steps ago. The name, transformer, comes from the fact that it transforms one sequence into another. In our case, we're transforming an input sequence 1, 2, 3, 4, 5, 6 into a single output number, 7. This is a regression task, which means we only need the encoder part of the transformer. This is the famous diagram from the original paper. On the left, we have the encoder. It reads the input sequence. On the right, the decoder. It generates the output sequence one step at a time. You'll see boxes like multi-head attention, feed forward, and those curved arrows that say add and norm. For our stock prediction example, we only need the encoder.
Why?
Because we're not generating a sequence, we're predicting a single number. So we can strip away the decoder and attach a simple linear layer on top. This makes the architecture much simpler to understand and implement, while still capturing all the core concepts. Here's our encoder-only transformer. At the bottom, we feed in the sequence 1, 2, 3, 4, 5, 6, plus positional encodings. Then we pass through 2 encoder blocks. Each block contains multi-head attention, feed-forward network, and 2 add and norm layers. After the second block, we take the representation of the last position, that's position 6, which corresponds to the number 6, and we feed it into a linear layer that produces the final prediction. We're using 2 encoder blocks, 2 attention heads, and a model dimension of 8. These numbers are tiny compared to the original paper, which used 6 layers, 8 heads, and 512 dimensions, but they're perfect for learning our simple arithmetic pattern. Let's start with the very first step, input embedding. The numbers 1 through 6 are scalars, just single values. But neural networks work with vectors. So we need to convert each number into a dense vector of length d_model, which is 8 in our case.
How do we do that?
We multiply the number by a learnable weight matrix w_embed and add a bias. Initially, these weights are random, but during training they'll learn to map each number to a useful vector representation. In the code, it's a simple one-liner, embedded equals x, t, asterisk w_embed plus b_embed. This gives us a 1/8 vector for each input number. Here's a crucial point. The attention mechanism has no built-in concept of order. If you give it 1, 2, 3, and 3, 2, 1, they look identical because attention just sees a set of vectors. That's a huge problem for sequence data. The solution is positional encoding. We add a unique pattern to each position's embedding so the model can tell where each element belongs. The original paper uses sine and cosine functions of different frequencies. The formula is shown here. For position 1, the encoding is 0.84, 0.54, 0.01, 1.00, and for position 2 it's different. When we add this to the embedding, each position gets a unique signature. The model can learn to use these patterns to understand order. In our code, we precompute the positional encoding matrix once and then add it to the embedded sequence. Let me visualize what these positional encodings look like. Each position gets a distinct wave pattern, different frequencies across the 8 dimensions. The sine and cosine functions ensure that nearby positions have similar encodings, which helps the model learn relative positions. The final input to the encoder is simply embedding plus positional encoding. For position 3 with value 3, we add the embedding vector for the number 3 to the positional encoding vector for position 3. This combined vector is what flows through the rest of the network. Now we get to the heart of the transformer, the attention mechanism. The equation is deceptively simple. The attention function takes 3 inputs: query, key, and value. It computes the softmax of the product of Q and K transpose, scaled by the square root of D sub K. The resulting attention weights are then multiplied by V to produce the final output. But what do Q, K, and V mean? Think of it like a search engine. Q stands for query, it's what you're looking for. K stands for key, it's like the index or the description of what each position has. V stands for value, it's the actual content you want to retrieve. For example, if you query books about transformers, the search engine compares your query against the keys, book titles. The ones with the highest similarity get the most attention, and you retrieve the values, the actual book content, weighted by those similarities. In our code, we compute Q, K, and V by multiplying the input by 3 different weight matrices, W_Q, W_K, W_V. These weights are learned during training. Let's walk through the 3 steps of attention using position 6, the last number, as an example. Step 1. Compute similarity scores. We take the query of position 6 and it with the keys of all positions, then divide by the square root of D_K, which is 4. The result is a vector of 6 numbers. Notice the highest score is with itself, 8.8, and the next highest is with position 5, 4.3. This makes sense. The most recent numbers are most relevant for predicting the next one. Step 2. Apply softmax to turn these scores into probabilities that sum to 1. Now we have 63% attention to itself, 23% to position 5, 8% to position 4, and tiny amounts to the earlier positions. Step 3. Take a weighted sum of the value vectors using these probabilities. The output is a new vector that contains information from all positions, but mostly from the recent ones. This is how the model looks at the entire sequence when making a prediction. Instead of doing attention just once, the transformer does it multiple times in parallel. Each one is called a head. Each head has its own W_Q, W_K, W_V matrices, so they learn different kinds of relationships. One head might learn, look at the immediate previous number, while another head might learn, look at the number from 2 steps back. For our pattern 1, 2, 3, 4, 5, 6, that's very useful. After computing all heads, we concatenate their outputs and multiply by another weight matrix W_O to combine the information. In our code, we have 2 heads, each producing a 4-dimensional output, so the concatenated vector is 8-dimensional, matching our model dimension. After the multi-head attention, we pass each position's representation through a small feed-forward network. This network is the same for every position, and it's applied independently. The architecture is simple. Expand from 8 dimensions to 32, apply a ReLU nonlinearity, then compress back to 8. The expansion gives the model more capacity to learn complex patterns like the rule, add 1 to the previous number. The equation is shown here. The feed-forward network of X is computed by first multiplying X by W1 and adding B1. Then a ReLU activation is applied, which takes the maximum of 0 and the result. Finally, the output is multiplied by W2 and B2 is added. The ReLU activation, max with 0, introduces nonlinearity, which is essential because without it, the whole network would just be a big linear transformation. Now look at the curved arrows in the diagram. Those are residual connections. The idea is simple. Before applying layer normalization, we add the original input back to the output of the sublayer. So for attention, we do x plus attention x, then layer norm.
Why?
Without residuals, the gradients can vanish as we stack more layers, making training impossible. With residuals, information can flow directly through the network, bypassing the nonlinear transformations. Layer normalization then stabilizes the activations by centering and scaling them to have zero mean and unit variance. It has two learnable parameters, gamma and beta, that let the model undo the normalization if needed. In our code, these two steps, addition and layer norm, are implemented explicitly after both the attention and the feed-forward sublayers. Putting it all together, a single encoder block looks like this. Starting from the input, we do multi-head attention, then add and norm, then feed forward, then another add and norm. The output of the block has the same shape as the input, 6 positions by 8 dimensions. Our model uses 2 such blocks stacked on top of each other. Each block can learn different levels of abstraction. The first block might learn simple patterns like adjacent numbers are related, and the second block can learn the arithmetic progression. This modular design is what makes transformers so powerful and scalable. After the last encoder block, we have a 6 by 8 matrix, 1 vector for each input position. But we only need a single number as output. Which positions vector should we use? In our task, predicting the next number, the most relevant information is in the last position because it represents the most recent element. So we take the vector for position 6, which is a 1 by 8 row. Then we apply a simple linear layer, multiply by a learned weight vector w_out, 8 by 1, and add a bias b_out. This gives us a scalar prediction. In the original transformer diagram, this would correspond to the linear and softmax layers at the top of the decoder. But since we're doing regression, we don't need softmax. We just output the number directly. Let's trace the number 6 through the entire network to see what happens. I've put the actual numbers from a trained model here. First, embedding. 6 becomes a random-looking 8-dimensional vector. Then we add positional encoding for position 6. That gives us the input to the first encoder block. In encoder layer 1, multi-head attention produces a new vector. We add the residual, then feed forward, then another residual. The numbers change, but the dimension remains 8. After layer 2, we get the final representation for position 6, a nice normalized vector. Finally, we multiply by w_out and add b_out to get 6.9999, which rounds to 7. This is how mathematics transforms the input into the correct prediction. Now let's look at the actual MATLAB code that implements everything we've discussed. I'll walk through the key parts. First, we set up the problem. X is our input sequence. Target is 7. Then the hyperparameters. d_model equals 8, number_heads equals 2, d_k equals 4, d_ff equals 32, number_layers equals 2, learning_rate equals 0.01, and we train for 2000 epochs. Next, the positional encoding function. It uses nested loops over positions and dimensions, applying the sine for even indices and cosine for odd indices. This is a direct translation of the mathematical formula into code. Notice that we pre-compute the entire PE matrix once, because it doesn't change during training. Here's the attention function. It's only 3 lines. First, compute the scores using matrix multiplication and scaling. Then apply softmax row-wise to get attention weights. Then multiply by V to get the output. This function also returns the attention weights, so we can visualize them later. The multi-head attention function loops over each head, computes its own Q, K, V, calls the attention function, and then concatenates the heads. Finally, it projects the concatenated result using w_o. This is the beauty of MATLAB. With matrix operations, we can implement the entire attention mechanism in just a handful of lines. The encoder block is the most important part. We start with x_current, which is the output from the previous layer or the embedding. We store a copy for the residual. Then we compute multi-head attention, add the residual, and apply layer normalization. That's the first add and norm. Then we do the same with the feed-forward network. Compute FFN, add the residual from before the FFN, and normalize again. This entire block is repeated number_layers times. In our case, twice. After the final block, we extract the last position and apply the linear prediction layer. All of this is inside a custom training loop that uses gradient descent to update the weights based on the mean squared error loss. After 2,000 epochs, our model converges beautifully. The loss plot shows exponential decay. It starts around 1, then drops to 10 superscript 1, 10 superscript 2, all the way down to less than 10. That means the predictions are incredibly accurate. And here's the final result. The model predicts 6.999987, which is essentially 7. The error is only 0.000013. That's 99.9998% accuracy. Keep in mind, we only trained on 3 examples. 1, 2, 3-4, 2, 3, 4-5, 3, 4, 5-6. The model generalized to predict 4, 5, 6-7 perfectly. That's the power of the transformer. One of the coolest things about transformers is that we can visualize what the model pays attention to. The bar chart shows the attention weights for position 6 after training. Notice the pattern: 50% attention to itself, 30% to position 5, and 10% to position 4. The model has learned that the most recent numbers are the most important for predicting the next one. This is exactly what we want. The attention mechanism has automatically discovered that the sequence is arithmetic and that the immediate predecessor carries the most information. You can extract these weights from our code by capturing the attention_weights output from the attention function. Let's recap the 4 core components of a transformer. First, positional encoding. It adds order information to the input. Second, multi-head attention. It allows the model to weigh the importance of different positions. Third, feed-forward networks. They learn complex patterns independently per position. Fourth, add and norm residuals. They enable training of deep stacks. Why are transformers revolutionary? They process all positions in parallel, capture long-range dependencies directly, are highly parallelizable, and scale well to long sequences. That's why they've replaced RNNs in almost every sequence task. Our model, despite its tiny size, successfully learned the arithmetic pattern and predicted 7 with near-perfect accuracy. Here's a quick comparison between the original transformer and our simplified implementation. The original uses 8 heads, 6 layers, d_model equals 512, and d_ff equals 2048. That's huge. Our version uses 2 heads, 2 layers, d_model equals 8, d_ff equals 32. Much smaller but perfectly suited for our toy problem. The original is trained on millions of words. We trained on just 3 examples. Yet the underlying mathematics and code structure are exactly the same. So once you understand our code, you can scale it up to real problems. Now that we've seen the complete mathematical implementation from scratch, let me show you a much simpler approach using MATLAB's built-in transformer layers. This comparison will help you understand why the built-in functions are so powerful and when you might still want to implement things manually. Let me walk through this new code line by line. We create a longer sequence from 1 to 20, and we'll use a sliding window of size 3. This means we look at 3 numbers to predict the next one. This loop creates our training pairs. For example, input 1, 2, 3, output 4. Input 2, 3, 4, output 5. And so on, up to 17, 18, 19, output 20. This is the key difference. With just 7 lines of code, we've built the same encoder-only transformer that took us over 300 lines in our manual implementation. This single line creates the skip connection that took us several lines to implement manually. It connects the input directly to the addition layer, bypassing the attention mechanism. That's the residual path we talked about. Instead of writing our own training loop with gradient descent, we just specify the optimizer, atom, number of epochs, and learning rate. MATLAB handles everything else internally. One line. That's it. The entire training process, forward pass, backpropagation, weight updates happens here. We test on the last few examples. 15, 16, 17 should predict 18, 16, 17, 18 predicts 19, and so on. Now let me show you a direct side-by-side comparison of the two approaches. This table tells the whole story of how much work MATLAB's built-in layers save us. So here's what this table really shows us. The manual implementation is like learning to drive a manual transmission car. You have to coordinate the clutch, gear shift, and accelerator. It's harder, but you truly understand how the car works. The built-in implementation is like an automatic transmission. You just press the gas and brake. It's easier, but you might not understand what's happening under the hood. The best approach? Learn with manual first, then use built-in for real work. That's exactly what we've done in this video. You now understand the mathematics, so when you use self-attention layer, you know exactly what it's computing inside. So which approach is better?
Both.
If you're building a production system, use the built-in layers. They're optimized, tested, and efficient. If you're learning or doing research, implement it manually at least once. Understanding the math will make you a much better deep learning engineer. The beauty of MATLAB is that you can start with the manual implementation to learn, then transition to the built-in layers for real applications. And everything from the math to the code is consistent and transparent. That brings us to the end. Thank you so much for watching. I hope this deep dive into the transformer architecture and its MATLAB implementation was helpful. If you have any questions, please leave them in the comments below. Don't forget to like and subscribe for more deep learning tutorials. The complete code is available on my GitHub, link in the description. Remember, in the world of transformers, attention is all you need. I'll see you in the next video.